So hello everyone, this is lecture 3 for the nuclear physics. In the last lecture, we have studied that how can you find the radius of nuclei using the concept of distance of closest approach. In this, there was a scattering of alpha particles from the gold foil by the Rutherford, and we use this method to find the approximate idea of the radius of the nuclei. So we will see a new method for the radius of nuclei, that is mirror nuclei method, and this is very helpful and the precise version. So this is the method to find the nuclear radius of the pair of mirror nuclei. So first we need to understand that what are mirror nuclei. Okay, so there are a few examples like carbon and nitrogen. So they have the same atomic mass, and the difference means these are the three properties are there which must be satisfied to call them as the mirror nuclei. That is, pair of mirror nuclei has same number of A, that is mass number. So A must be same. You have example potassium, calcium 39, 39, lithium, beryllium 7, 7. Number of neutrons and protons are exchanged in this pair. So it is seem like that they exchange the number of protons and neutrons. See here, protons are 6 and neutrons are 7. Here protons are 7 and neutrons will be 13 minus 7, that is 6. So they will be exchanged. So number of neutrons and protons are exchanged. And difference between the neutron and the pure proton is always plus minus 1. So see, 6 minus 7, 19 minus 20, 3 minus 4, that will always be plus minus 1. So these three properties will give you the mirror nuclei. So we will take an example like potassium and the calcium. So you will see that it is 39, 39, atomic number is same. And if you see that here it is 19 and 20 will be the protons, and here proton will be 20 and neutron will be 19. So they are exchanged. So that's how you can see this. So I hope you understood the definition of the mirror nuclei. Now let's see that how can you find the radius using this mirror nuclei method. So we will take the example as nitrogen is means nitrogen atom is converting to the carbon atom. So it is 713 will give you 613. So proton is decreasing and proton number is decreasing. So beta plus particle will be emitted with the neutrino. Okay, so if it will be beta negative, it will be anti-neutrino. So we'll understood that later. But you must remember that when proton is means proton is decreasing by 1, that will give you beta plus with neutrino. And when proton is increased by 1 and this will atomic number or mass number is decreased by 1, then you will see that beta negative will be emitted. So we'll see them. But here our task is to calculate the radius of the nuclei, because we know radius of the depend means upon what the radius is depending. It is on the atomic mass number, that is R equal to R naught A1 to the by A to the power 1 upon 3. So we know that A must remain, if A remains same then radius will remain same. So you can see that A is same in all the three cases or all the mirror nuclei. So if we can find the radius through this method, that will same for the K or Ca or Cn, means they will remain same. So let's take an example, that is N is converting to C. So it is 7, 6 beta plus neutrino is emitted. Now see how you can find the change in energy, means how much energy is emitted in this reaction. That will be given by these three formulas. You must remember them as it is. And this concept is very important according to the exam point of view. So you must remember. So daily equal to M parent minus M daughter. So parent is this, mass of this minus mass of this. So that will give you total energy released. Means this mass defect will give you energy release. So delta is also equal to means total kinetic energy of products minus total kinetic energy of reactants. That will give you the energy amount which is released. Or means it will depend. If it is positive, then it will be released. If it is negative, then it will be absorbed. So daily also can be given by the binding energy of daughter nuclei, that is this, minus binding energy of parent nuclei. Now see, binding energy is related with the binding of the nucleons. So if these particles are there, so there will be no binding energy for them. It will be for carbon and nitrogen. So binding energy difference will be binding energy of carbon 13 minus binding energy of N13. So it will not for the particles, it will for the when there are nucleons which are binded. So it will be given by this formula. So remember them as it is. And if this value comes out to be positive, then energy will be released. And if this value comes out to be negative, that means energy will be absorbed. So you must remember them. Now how can we find this energy difference? If we want to use this formula, that is binding energy of carbon minus binding energy of nitrogen, so we must know the formula for the binding energy. So in the future we will see that there is this model, liquid drop model, which gives us this empirical formula for the binding energy. And this is the very much accurate formula. Here this EV is the main term and these all four are the correction terms. So we call it as, we will understand this in the detail in the future, but here just remember this formula. So binding energy of nucleus is volume energy term minus the surface energy term, Coulomb energy terms, asymmetry energy term, and this is pairing energy. Okay, so this is the formula. Now this EV is given by AV, this is some constant A is this mass number, minus AS e to the power 2 upon 3 minus AC Zc, that is atomic number of carbon, Zc square a1 upon 3 minus Ac, a minus 2 Zc divided by a square plus minus delta by a to the 3 by 4. So this is for the carbon binding energy. Now we need to put the value in this. We need this for nitrogen also. So we'll just put it here. ABA. A is same for both carbon and nitrogen. That's why it is remaining as it is. In place of Zc, we'll write Zn. Zc, we'll write Zn. And this is plus minus delta by a3 by 4. And we already know from the last lecture, a minus 2z is nothing but the difference between the neutron and the proton. So that is 1 here in the mirror nuclei case. Now if we find the difference c minus n, so this will cancel out, this will cancel out, and this term also cancel out because this is nothing but plus plus minus 1. That will give you same value here also and here also. So this will also cancel out and this will also cancel out. So this is simply the difference of Coulomb energy terms, means Coulomb energy for carbon and Coulomb energy for nitrogen. So here we can write this delta E is nothing but ACN minus AC carbon, and we will write it as E1 minus E2. Now see what is this delta pairing energy term. This will be plus for the even nuclei when proton and neutron are even, and this will be minus for the odd nuclei, because when it is even then it will give you extra stability in the nucleus, and when stability is large then binding energy will be large. That means it must be added, this term must be added. When stability is less, that means this term must be negative, so it will be odd. So we'll see this also in the future. Now we know this is Coulomb energy difference simply. So Coulomb energy formula for the nuclei is given by this: E square by 4 pi epsilon naught 3z square by 5r. So normally we use this formula to calculate the binding energy. In place of z, just write the atomic number of that particular material. So this is the formula, but to be precise, this will be the exact formula, and this came due to the screening effect. Okay, so normally we use this formula. So the difference delta E will be given by E1 minus E2, so it will be Z1 minus Z2, Z1 square minus Z2 square. So this will be your delta E square of 4 pi epsilon naught 3 Z1 square minus Z2 square divided by 5r. Now we just substitute the value of delta E here, and we know Z1, Z2, and we can calculate the R. And R is radius of both the nucleus. That will remain same because R depends on the 8. So that means this R will remain same for both the nuclei. So that's how we can find the radius. So there is this another way also to see this whole thing. So how you can see this? Here this number of proton are decreasing, and you can see that then this beta particle is emitting. So we can write it as this. Means see here this number of protons means here you can see this is 6 plus 1 7, and here number of neutrons are 6. So here 7 we can write 6 plus 1, and here protons now becomes 6 and neutrons are 6 plus 1. So you can see that you can just see this as proton is converting to the neutron. So now if it is the case, then we can write this equation as P n plus beta plus neutrino. So this reaction is occurring here. Now we need to see that. Now see, whatever the energy is released in this process, or we observe the energy, that is not equal to this delta E energy. So what is the meaning of this? Means some energy is utilized somewhere else. So here you can see that mass of neutron is greater than mass of proton, and this is also the electron, or you can say positron. So there will be mass of these two particles, and we consider that neutrino is massless. So there will be energy utilized to increase or create the mass for this neutron, means the difference, and this positron, and then the remaining energy will be released, which we observe as delta E, or not the delta E, the observe in the experiment. So that's how we observe the energy which is less than this delta E. So here is the expression: whatever energy should be released due to the change in the binding energy, a part of this energy will be utilized in the reaction to take place in the forward direction. So the part of this delta E energy will be utilized to create this mass. Which mass? This n minus p, mn minus mp c square, and this me c square. So this mass of electron and this difference between this proton and neutron, because neutron mass is greater. So the energy will be utilized to create this mass and this mass, and remaining will be observed by us. That is the kinetic energy of the neutrino or the beta particle. So that will be a mix of both these particles because they both contain the kinetic energy. So this energy will remain fixed, means some of these energy will remain fixed, as means you can see that this nuclei coming from here to here, and the particles are emitting with the energy, and that energy will remain fixed, and that is kinetic energy. But this energy will be distributed among them, means beta plus and the neutrino, the energy will be distributed, and that is given by the Fermi's theory of beta decay. And if we see that now how can we means solve this thing, because this energy will always be distributed, means we can never know that how much energy for the neutrino, how much energy for the beta, but we know the total energy. So how can we find that? So this is the energy spectrum of beta decay. Now see, there are 2 points when this beta particle consuming zero energy, and then if beta energy of beta particle is zero, the neutrino will have the maximum kinetic energy, and if the maximum kinetic energy is contained by the beta particle, the neutrino will have the zero energy. So this is the extreme cases when beta particle is zero, and this k beta max, and this k beta max is contained by the beta particle, then this neutrino will have the zero. Means sum will always remain constant for the beta and the neutrino. When beta have zero, the neutrino have maximum, and when beta have maximum, this neutrino have zero. And between this there are infinite possible combination for the kinetic energy. So what is the solution? We can experimentally find very easily this maximum kinetic energy for the beta particle. So we'll use this case now when this neutrino have zero. So we can write this reaction in terms of MEC square. In place of this kinetic energy, we'll write the k beta max, because this energy will remain constant. Okay, this sum will always remain constant. That's why we can just simply write this equation now, and we can also find this value also very easily in the experimental way. Now what is this delta I? We know from here this formula gives you delta I. So just substitute value here, and you know these things. Now this equation will become this, and now we know the value of E square for pi epsilon naught. You must remember these numbers, some small number, that is 1.44 mega electron volt Fermi, and you know Z1 Z2 Mn minus Mp. This is the one proton and one neutron difference. This is also constant. You must remember this number, 1.29 mega electron volt, and MEC square, this is 0.51 mega electron volt. You must remember these terms, and you know you can find this value from the experimental basis. And now only thing is unknown is r. So from this equation you can calculate the r. That will be very much exact value for the radius of the nuclei. So in the next section we will see some examples based on this, and all kind of question can be framed from here. Then we will see the nuclear probes, and nuclear probes are nothing but means probe is something investigation. So when we investigate a nuclei using a radiation beam or anything, so that's what we study in the nuclear probes. So we'll see that. Okay, thank you everyone.